Well, hello, it's Mr. Suker again. A little bit of an extra credit project here. I mentioned in class that I was going to stick with fairly plain English explanations for the different ways that we describe electron locations in the electron cloud. We probably, hopefully by this point, have talked about something like this, with the numbers representing the principal quantum numbers and then the sublevels and designating electrons in specific orbitals within those sublevels. And that allows us to produce an electron configuration that looks something like this. Hopefully you can recognize this electron configuration as being for the noble gas neon. Know it's a noble gas because it ends S2P6, the noble gas configuration. And what I want to do is clue you in a little bit more to the technical terms that we use for designating the locations of electrons, and then we'll also talk about a little bit of an extra credit, small extra credit assignment to go with this. So we talked about principal quantum numbers, and as the term principal should indicate, it is a main quantum number, and this suggests that there are other quantum numbers. And in fact, there are a total of 4 quantum states that are required to identify the location of any specific electron. So there really are 4 things that you need to know, and they're very similar to what we talk about when we do a traditional electron configuration, in that we need to designate the sublevel, and then within each sublevel there's different possible orbitals, the S having 1 spherical orbital, and then the P having 3 different hourglass-shaped orbitals in each of the 3 primary directions, x, y, and z. So we need the principal quantum number, we need the sublevel, we need which one of those specific orbitals, and then finally some way to indicate the up versus the down in terms of the electron spin. If we get into a little bit more of a technical description of it, we see, I got to figure out which way I need to move. We see what we end up with is something, hey, there we go, that looks like this, where we have our 4 quantum numbers, N, L, M, and S. N stands for the principal quantum number. That's the same number that we have, so it starts at number 1 and goes in whole integers, increasing 1 at a time with no theoretical upper limit to it. We do know that we only know of 7 principal quantum numbers on our current periodic table, but that doesn't mean there couldn't be an 8th, 9th, or a 10th that we discover eventually. So we have our principal quantum numbers here. Our second quantum number is called the angular quantum number, and it gets the symbol L. I don't know why we chose L for angular, but you know, something lur, L, don't know. But so we get L is a sequence that goes from 0 to n minus 1. So L is a function of n. So if you are at principal quantum number 1, then the only value of L that you're going to have is 0, because this sequence stops at n minus 1. 1 minus 1 is 0. For principal quantum number 2, you would have L values of 0 and 1, stopping at 2 minus 1, which is 1. So principal quantum number, angular quantum number, and then the magnetic quantum number. And the magnetic quantum number can go from negative L through 0 to positive L. So in the case of L equals 0, the only value that you could have for M is 0. For L equals 1, then you have 3 possible values: negative 1, 0, and positive 1. Everything here is whole number, everything here is integers. M is the only one that can be a negative or a positive number. And then we have the 2 possible spin states, which in quantum number notation, instead of being called up and down, we call it positive 1/2 or negative 1/2. So at any particular combination of N, L, and M, you're going to have 2 electrons, one of them in the positive 1/2 spin state and the other one in the negative 1/2 spin state. So these three quantum numbers up here, principal, angular, and magnetic, are said to be the quantum numbers that identify the orbital. So this will take you down from principal quantum number through sublevel and orbital, and then to identify a specific electron, the last piece of the address would be this spin state of positive or negative 1/2. So let's see how that works out to designate the potential addresses for specific electrons. So let's start with a case where we have an electron that's located in the first quantum level. So at the first quantum level, n is 1. The only possible L value for an n of 1 is 0. And the only possible magnetic quantum number for L equals 0 is 0 itself. So for n equals 1, this is the only possible combination of three quantum numbers to designate the orbital. Then each electron can either be a positive 1/2, an up 1/2, or a negative 1/2, a down 1/2. So this gives us a possibility of 2 electrons located in the 1, 0, 0 orbital. If we bump that up a notch then, and we look at n equals 2, we start to get a significant number of additional possibilities. So again, we have our 2, 0, 0. But now I can also have an L value of 1, because L goes from 0 to n minus 1. So 2 minus 1 is 1. So I have L values, and then my L values can be negative 1, 0, and positive 1, from negative L to positive L. So here I have 4 possible orbitals. One is a 0 angular quantum number orbital, and the other one is, or the other 3 are angular quantum number 1 orbitals. And within those, I can have 2 electrons, one in the positive 1/2 and one in the negative 1/2. So each of these can be 2. So 2, 4, 6, 8 total electrons for principal quantum number 2. We take a look at how this kind of exponentially grows. This is what the third quantum level looks like. I'll give you a minute to look it over and see the pattern. We repeat our L equals 0 and our L equals 1. So here's our 8 electrons that we had before. And then we add in the angular quantum number 2. That goes from, they're a little out of order here, but they go negative 2, negative 1, 0, 1, and 2. And then again, for each one of these individual orbitals, each designated by 3 quantum numbers, we can have 2 electrons, one in the up 1/2 and one in the down 1/2, positive, negative 1/2 spin state. So you can count then how many electrons we would be able to fit in the third principal quantum number by adding all of these up. So this probably should sound a lot like what we talked about in class. In class we used a little bit more plain English. Here we're using the thorough quantum number representation. It really is part of a pattern. Remember, what we're trying to build on here is this idea that the electron structure is a repeating pattern, and there's a word that we associate with repeating pattern, and that is periodic. And so that all ties together. So as a little bit of an example, what I'd like you to do for a little bit of extra credit is relate what we talked about in class with the SP, D, and F orbital, or SP, D, and F sublevels to L, and explain why you know it. So SP, D, and F, how do they relate to these values of angular quantum numbers 0, 1, 2, and 3, and explain how in a diagram such as this you can know which one of these is S, which one of these is P, which one of these is D, and which one of these is F. So see if you can work that out. And also for bonus, see if you can write out all of the possible quantum number combinations for our next principal quantum number n equals 4. So that would be the next step up. What would the card look like if you were to write out all the principal quantum numbers for n equals 4? Tell you what, to make it fun, write your answers on an index card, turn this into me by the due date given in the Veracross posting, and I'll give you a little bit of extra credit for going fully technical, fully nerdy on our discussion of principal quantum numbers. So until then, I will see you in class. Have fun.